we can replace in omega n, we can get the relation of Vt over Kfi minus Ra plus R rheostat over Kfi squared multiplied by torque. So R rheostat here is the added resistance. Okay, if we add zero resistance, so this means that the omega will be the natural curve, which is this one. This is called natural curve, okay, or natural characteristic. If we added resistance, what will happen? According to the no load speed, as you can see, it's independent of the resistance. So whatever the added resistance, the no load speed will be constant. However, for the resistance, for the speed at any other point where there is a value for torque, you will find that the R rheostat is effective and the speed will be changed. Right. As you can see in the figure here, Shabab, at certain load torque T asterisk, assume this is the rated torque. So in this case, you can find that we have, assume this is at R1, this is at R2, this is at R3, and all of the resistances R3 is greater than R2 is greater than R1, which means added resistance to the armature. And as you can see, each point will have different speed. Tamam? If we compare or may extend the line from this point to here, you will find that the speed is different. مظبوط يا شباب؟ So we can now control the speed by adding resistance. But the question, is it wide range of speed control or not? Which means if we apply lower load torque, وليكن for instance the load torque is like that, torque load 1, and this is torque load rated for instance. If the speed range wide like the speed range at high torque, يا شباب?
No.
It's not wide range now. So this is a drawback for the adding resistance technique. It's not preferred with the small value of load torques. تمام يا شباب? So it's not wide range of speed control. This is one of the drawbacks. Another important drawback or general drawback is the losses. Now, if you add extra resistance here, again, if you have extra resistance, okay, added extra resistance, the amount of total resistance will be increased, which means the power losses will be increased. So it's not preferred to control the DC motors using adding resistance, because of the losses will be increased and the efficiency as well will be decreased. So these are, Shabab, the three different methods now. So we have voltage, field, and adding resistance. So in general, we said in voltage control, we cannot increase the voltage overrated. And also for the field control, it's not preferred to decrease the field where the load torque is constant, because it may overload the machine at the field weakening part. So the best way to control the DC motors is to control the machine under the rated speed, where the torque will be constant and voltage can be used as controller. So we can use voltage control and add the speed lower than the rated speed. So this zone now, شباب, we prefer to use voltage control at this zone. Okay, شباب? And we should make fixed torque. So we control the torque in order to be constant value. And when the speed is higher than the base speed, so it's better to make the control to keep the power constant. Okay, you can use now field control. However, you have to check the power. The power has to be constant. For that, the torque will be reduced like that by increasing the speed. So this is the best way to control the DC motors. An example here for this method of control, variable speed drive. Variable speed drive يا شباب, this name is given for the machine with power electronic converter. So the word drive means machine plus power electronics converter. Yani both of them together are called drive system. And because the power electronic can increase or decrease the speed, so it's called variable speed. Okay, شباب? We have variable speed drives as DC drives and AC drives. For DC motor, for sure we use DC drive, and for AC motors we use AC drive. Right. So we have here variable speed drive system uses a DC motor that's supplied from a variable voltage source. So the aim of power electronic converter here is to achieve variable voltage source. The torque and power profiles are shown in the figure below. So this is now the torque and power profile. So we should respect the base speed. If the speed is lower than base speed, we should keep the torque constant. And if the speed is higher than base speed, we should keep the power at constant value. Type. The drive speed is varied from zero speed to 1500 RPM. So this is now the range of speed control, where 1500 is the base speed, by varying the terminal voltage from 0 to 500 volt. So this is the way to control the speed below the value of or less than the value of base speed. Okay, شباب. طيب. What's required here in this region? It's required to determine the motor armature current if the torque is held constant at 300 Newton meters. تمام? Up to the base speed. So we need to fix the motor speed. Sorry, we need to fix the motor torque at 300 Newton meter, whatever the value of speed. So this means the power is going to be variable, torque is going to be constant, okay, and in this case we will use voltage control. So what will be the value of torque now? We have range from 0 to 1500. So let's assume one operating point to operate the machine and find the corresponding torque. Simply, شباب, we have the base speed, which is 1500 RPM. We can get the K5 value from the no load speed point. So we can say K5 equal V terminal over omega multiplied by 2 pi over 60. N multiplied by 2 pi over 60 in order to get the value of omega. We know omega or speed in radian per second equals speed in RPM multiplied by 2 pi over 60. So in order to get K5, we divide V terminal, because we assume that at no load the current will be very small. So we can say that no load speed attains at the value of V EF equal V terminal or EA equal V terminal. So we can get the value of KFI like that. Fine. Now, we know the value of torque. We need to keep the torque constant at 300 Newton meter. And we got the value of K5, so simply we can now calculate the value of current. So the current, which can be drawn in order to keep the machine at constant load torque, equals T over K5, which is now 94 ampere. Right. So this was the first part, the motor armature current at 300 Newton meter torque. Number B, the speed beyond the base speed, which means when the speed is higher than omega base, is obtained by field weakening. Field weakening, يا شباب, we discussed this before. The meaning of field weakening means we are going to decrease field current. So decreasing field current will lead to increase the machine speed. So we are going to now make field weakening, where we are going to increase the speed at this region. So we expect to keep the power constant, and we expect the torque will be reduced. Right. What's required here? The speed beyond the base speed is obtained by field weakening, while the armature voltage is held constant. It has to be constant, شباب. Otherwise, the machine may be damaged. We shouldn't increase the voltage anymore. Also, we can control the machine using a field and keep the power constant. So we expect in this case, شباب, if the voltage will be constant, so we expect the current also will be constant because the power will be constant. What's required here? Determine the torque available at speed of 3000 RPM. طبعا يا شباب it's stated here the torque available. What is the meaning of torque available? Torque available from the expression here means you don't know what will be the value of the torque. You don't have certain operating point in order to say I should maintain the torque at fixed value or constant value of torque. Why? Because if we fix the power now and we increase the speed, the torque will be decreased. So the target here after or higher than the base speed is to get certain value of speed, whatever the value of torque. For that, it's stated here, find the suitable or available torque, because we will fix the machine power. Right. For that, شباب, we have a speed of 3000 RPM. Power is constant, and we need to calculate the machine torque. Considering that, we are going to neglect all of the machine losses. So simply, شباب, now for field weakening at speed of 3000 RPM, in order to get the value of nu phi, or neglect the voltage drop across the resistance. So we can say now the copper loss is neglected, and we may say V terminal equals EA equals 500. So this is the assumption of neglecting losses. For that,
your mic is muted.
ما نسمعك دكتور.
دكتور ما نسمعك، المايك مقفل.
شباب, I don't know, my mic was muted.
Yes, I can hear you now.
Yes. Oh, we can hear you.
I don't know what's happened. But from which instance, شباب, my mic was muted?
2 minutes.
2 minutes.
Just less than a minute.
This slide, did
Yes.
you, from the beginning of this slide,
No,
Yes,
it's B.
number B?
Yeah, that's B.
Okay. Time. Again, in order to calculate the speed, شباب, it's required to calculate the speed when, it's required to calculate the machine torque when the speed is increased to 3000 RPM. تمام? So we can assume now that V terminal equals EA because the losses are neglected, which means the resistance also can be neglected. So to simplify the solution and obtain the value of KFI, we can assume now that the losses on resistance are neglected, or the voltage drop also on resistance is neglected. So we can say V terminal equals EA, equals the supply voltage of 500 volt. So we can say Ka phi equals 500 over speed in RPM multiplied by 2 pi over 60 to get it in radian per second. And this is now the value of Ka phi. Now simply we have the value of current because the power is constant, and this means that the current will be constant and voltage as well here. So we can say torque equal K phi, which we have already calculated, multiplied by the same value of current. So this gives you the value now of the new torque. As you can see, Shabab, the torque is 150 Newton meters. Before, the torque was 300 Newton meters. So this only comes due to the reduction in flux or field weakening. تمام يا شباب? So this is an example for the speed control using constant power before the or below the speed. Constant volt below the base speed, and constant power beyond the base speed. Okay, شباب. Now, شباب, for the series motor, we discussed now separately excited and shunt. We have another type of motors called series DC motor. What is the difference between series and shunt? You know, series means we are going to connect the machine field winding in series with the armature winding. So as you can see here, Shabab, this is our series winding. It's going to be connected in series with the armature winding. And also we will add another resistance here, or rheostat, in order to control what? Control current, control machine speed, and so on. Tamam? Right. What will be the difference now? Is there any difference in regard the relations? You know, field winding is responsible for the machine flux. Now, before, in separately excited, for instance, the field current was supplied from another source, and it was fixed. However, here in this machine now, the field current equals to the armature current. So in our equations, we should consider that IF equal IA. This means, ya shabab, for the value of Ka phi, it can be represented that, for instance, Ka multiplied by another constant multiplied by IF. And you know, IF equals IA, so we can combine these two constants now to be K series multiplied by IF, which is the same as armature current. So we have here now a new constant. This constant is called K series. Now, in all of our relation, we should replace Ka phi, replace all of values of Ka phi from omega, from EMF relation, from torque relation. We should replace Ka phi by K series IA. Let's start from EA. You know, EA equals Ka phi multiplied by omega. So replace Ka phi by K series IA multiplied by omega. For the torque, similarly, torque was, for separately excited, torque was Ka phi multiplied by IA. So replace Ka phi by K series IA. So the relation now will be K series multiplied by I squared. So these are the relations now for EMF and torque. For the relation of speed, you know, from here we can say that omega M equals EA over K series IA. Now we can replace EA by Kirchhoff voltage loop here from this circuit. So we can say EA equals V terminal minus IA multiplied by all of series resistances. So we should include R series, which is the field winding series resistance, and R rheostat, which is the control resistance, in addition to the value of armature resistance. So this is now the Kirchhoff voltage loop. So simply E equal V terminal minus IA multiplied by summation of the three resistances. And from here, we can say that omega M equals Vt over K series IA minus summation of series resistances over K series. So this will be the relation of omega M. Now, if you would like to draw the characteristic, which is the torque speed characteristic of the machine, simply you can use any MATLAB or any code using MATLAB program, for instance, and start change the value of t from very small value to the rated value, for instance, and record the corresponding value of omega. In this case, you will have a waveform like that, this shape يا شباب, at zero rheostat. And if you increase the value of rheostat or control resistance, the characteristic will move in this direction. So this is the way of speed control for series motor using adding resistance. Type. From the characteristic here, Shabab, we can say that at small value of speed, which means at the starting of the machine can support high torque load. صح يا شباب? As you can see, the torque here is very high compared to previous types of motors like separately excited and shunt. So this is here one of the important advantages of series DC motor. Because we have some applications, we need high starting torque in order to operate the machine. And after that, once you operate the machine, the torque can be reduced after that. This is like شباب, like cranes, like cars, like mixers, like any kind of load that has high starting torque, and after that the torque can be reduced. Type. Like blenders as well in home appliances. Okay. Right. In home appliances, we have already blenders using series DC motor. However, it's connected to AC supply. So we can connect the series DC motor to AC supply, but in this case we call it as universal motor. Universal motor is nothing but DC series motor and supplied from AC supply. So this is the universal motor which exists in our home appliances like in blenders. تمام؟ as an example for blender, you have high starting torque. You add the objects in the blender in the beginning, so you have high starting torque. After that, if the objects inside the blender start to be cut, so it will be very small and the torque will be reduced after that. Okay, so this is one of the examples for the series DC motor application. Right. Is there any question, Shabab, regarding the meaning of DC series motor and the application? Okay. Now let's have numerical example about DC series motor. We have a motor of 220 volt, 7 horsepower, series motor, is mechanically coupled to a fan. What's the meaning of fan, ya shabab? Or fan load. What's the meaning of fan load? Fan load means all of time that the torque is proportional to square of the speed. Fan load like what? Like what? We have the load called as fan load if it's like fans, any kind of fan, or bumps. Okay, so fan and bumps are considered as fan loads where torque is proportional to omega square. So we can say T1 over T2 equals omega 1 over omega 2 to power 2, like that. This is the relation between torque and speed for any fan loads. Okay. For this fan load here, the motor draws 25 amps and runs at 300 RPM when the motor is connected to 220 voltage supply with no external resistance. So this means that rheostat equals 0. The torque required by the fan is proportional to the square of the speed. طبعا we know this meaning because it's stated here that the load is fan type. يعني في انواع ثانيه يا شباب، يعني there are many kinds of load torques, okay, like traction load torque, like torque load constant, okay. يعني however we will state in the problem exactly what will be the relation between torque and speed if we specify a certain load torque. Right. So the torque required by the fan is proportional to the speed. We said that proportional to the square of the speed. RA equals 0.6. This is armature resistance. R series, this is the field winding resistance, equal 0.4 ohm. And neglect armature reaction and rotational loss. But before continuing, شباب, can you see here the value of field resistance? Field resistance equal 0.4 ohm. Do you remember the field resistance value for the shunt and series and separately excited problems or previous classes?
And they were around 50 or something.
Yes, exactly. It was 50 ohms. So what has happened? Why the field resistance now reduced? يا شباب. Why we reduce the field resistance here? يعني it became 0.4 ohm. يعني 0.4 compared to 50 ohms. يعني it's يعني a huge amount. It's 100 times or more than 100 times. Why we use here small resistance in the series field winding? Regarding the current يا شباب, what is the current in the shunt machine? What is the field current? Was it high or small current? شباب.
High.
لا, it's not high. Compared to the separately excited يا شباب, يعني for separately excited here in previous examples, the field current here will be very small compared to the armature current, because we stated that the aim of field is just to build up the flux. It's not the source of power. تمام؟ يعني field current or field power is not the source of power of the motor. It's just a way to convert power from electrical to mechanical. This is just to build up the flux. So the field current should be small. Okay? And here in this problem, the field current was 5 amps, and the current in the armature was varying from 100 to 300 amperes, which is very high compared to the field 1. However, in series here in our example, as you can see, the series resistance is 0.4 ohm. 0.4 ohm because now the series resistance is connected to this in series with the armature resistance. So the current which will flow in the field now is the armature current, which is high current. But if we have high current, can we use small cross-section resistance? Is it possible to use small cross-section resistance, شباب? Or the cross-section now has to be higher in order to support the high value of current? We have the relation of resistance R equals rho L over A. So the cross-section, if we have a small resistance, the cross-section will be the cross-section, if we have a high cross-section, the resistance will be small. And this is indication that you can flow a high current. However, if the cross-section is very small, this means the resistance will be high, and this can support small value of currents. For that, because here the field winding is connected in series with the armature and the current is going to be high, the value of resistance has to be small in order to have sufficient cross-section for the armature current. Fine. It's required here in part A, شباب, to provide the power delivered to the fan and the torque developed by the machine. طيب ازاي نحسبها يا شباب؟ Who can help me to solve this part? يا شباب, we need to determine the power delivered to the fan and the torque. How we can solve this part of problem? Who can help me يا شباب? Ali Hilal?
Yes.
Can you help me, Ali, in solving this part?
We can find the power used by the fan from the torque and the speed.
Type.
Or using the volt and amps.
Type. Do we have here torque and speed?
We only have speed.
We have speed only, تمام? And we also have volt.
Yes.
Volt. So can we get, and we also have current. So can we get it now be developed through EA multiplied by IA? Is it right?
Yes.
We have IA, so we need to calculate
EA.
EA, exactly. How we can calculate EA here? EA equals?
From it's the source voltage, which is 220.
Yeah, minus
the voltage drop across the resistance.
Exactly, so which are R series plus
and
armature. Thank you very much, Ali. So we can firstly start with the EA equals V terminal minus IA multiplied by the 3 series resistances. However, in case number 1, the rheostat value was 0. So simply we can calculate the value of E, and we have I, so we can now multiply E by I to get the value of A of power needed. Now, this value of power in watts, if you would like to calculate in horsepower, you should divide by 746 in order to get it in horsepower. Type. Now, we have now the A power. Also, it was required here to find the power delivered to the fan and the torque. Now we need to calculate the torque, and we have the value of power. So simply we can say now torque equals power developed over over speed. And we have the value of speed in RPM, so we should convert to radian per second first and get the value of torque. So here we can say torque equals power developed, which has been calculated here, which is power developed, over value of omega m. And you know omega m equals n multiplied by 2 pi over 60, and we calculated the power developed, so simply we can get the value of current. This is for number 2 or number B. The speed is to be reduced. طبعا يا شباب, for the series DC motor, this is here the characteristic of separately excited and shunt. If we added resistance, you will find that the speed will be decreased. And the same as well if you add resistance in series. So here you can add resistance or increase the value of rheostat in order to have other curves and reduce the speed of the motor. So it's required here to reduce the speed to 200 RPM. So it's expected to add resistance or to increase the value of rheostat. The question here is, the speed is to be reduced to 200 RPM by inserting a resistance RAE in the armature circuit. So what is the need required here? Determine the value of this resistance and the power delivered to the fan. So it's need now to calculate the value of R needed in order to reduce the speed and what will be the delivered power. Right. Regarding the value now, we have many things. Firstly, the current will be changed. Is it right or not? The current has to be changed because we added resistance.
Yes.
And the torque also will be changed because the speed is changed and the relation of fan load, torque is proportional to the square of fan speed. So firstly, in order to calculate all of these values, we need to get the value of series constant, which is K series. How we can get K series, شباب? Simply from the relation of torque. We know that torque equals K series multiplied by IA squared. But this is from the first condition. This is now from the first loading condition. So we could get the value of K series. We have the torque and the current. So simply we can substitute and get the value of K series. After getting K series, we can use it now in the second loading condition. In the second loading condition, we know the value of speed, which is 200 now, 200 RPM. And we would like to get what? We'd like to get the torque and the torque and resistance. Sorry, power or resistance. To get the value of power and resistance. But in order to get power, which is power developed, it's equal to EA multiplied by IA. So we need to calculate EA and IA. And also we can get the power from torque developed multiplied by omega. We have omega and we need to get torque. But we have another relation, which is torque is proportional to omega squared. So we can start with this relation to get the value of torque in the second case. So simply, torque load proportional to omega squared. This means that T1 over T2 equals omega 1 over omega 2 all squared. So simply we can get the value now at the value of torque at 200 RPM. So this is now, شباب, the value of torque. It's 68.9 Newton meter. Type. For now, we have the value of torque. We can calculate the power because we have torque and omega. And also we can calculate current from torque. So simply we can say that torque equals K series multiplied by IA squared. So here, this is the relation. Here, this is the relation of torque equals K series multiplied by IA squared. So we have K series and we have torque, so we can get the value of IA. The current is obtained here, 16.68 amps. So we got the current and we have the terminal. Can we get, and we have also, we can calculate EA because EA equals K series multiplied by IA multiplied by omega. So if we calculate EA and we have the current, we can now calculate the value of added resistance. So simply EA equals K series IA omega M. We have K series, we have the current, and we have the speed of 200 RPM. So simply we could obtain the value of EA. After getting the value of EA, we can apply Kirchhoff voltage law on the motor circuit in order to get the value of rheostat. So this is the way how we can get the value of rheostat. Then we need to calculate the power developed. Simply we can multiply EA by IA or torque by omega. It will give the same value. Any question, شباب, in this problem? Is it clear? Good. Another definition, شباب, needed in DC motor is called the speed regulation. Speed regulation, it's a matter of evaluate the machine in terms of how the machine can keep the speed constant. طبعا we know that if we load the machine, the speed will be decreased. However, if the speed decreased a lot, this means that this motor is not well designed. So we should test the machine and test something called speed regulation. Speed regulations equals the no load speed minus full load speed over full load speed. Okay, شباب? So we can get the no load speed طبعا by assuming that EA equal V terminal. We can get the value of no load speed. Okay, and for full load speed, we can get it from the full load operating conditions. Okay, or we can also calculate the speed, شباب, or speed regulation at any points of loading. It's not only at full load. And if we are working at half load, so we should get the speed at half load, okay, instead of full load. تمام؟ يعني we can say that omega no load minus omega load at any value of load. So it's the same way. Speed regulations equals this is multiplied by 100% also. تمام يا شباب. This is at any kind of of loads. Now يا شباب, for equation or for problem 4.8, we have calculated here, we have solved here in class. Let's calculate the speed regulation together. This was the problem 4.8, and we had two different operating points here. We have operating point at 1500 RPM and at 3000 RPM. Let's calculate the speed regulation at the value of 1500 RPM. How we can get it, شباب? It's speed regulation at 1500 RPM. And 1500, this one was the speed of full load. Okay. Hi شباب, how we can calculate? Sorry, base speed is no load. Speed of 1500 is the no load speed. So we have here the no load speed. Okay. So assume that we have another loading condition. Okay. So we have N no load equals 1500 RPM. And assume we have another load speed where N load equal 1400 RPM. So what will be the speed regulation now? We can say, شباب, who can solve with me?
Doctor, we will find the difference between them and divide it by the N load.
Exactly. طبعا we don't need here to convert from N to omega because it's ratio now. Is it right? And the ratio 2 pi over 60 will be the same in numerator and denominator. So we no need to convert now. So we can say now it's no load equals 1500 minus full load, which is 1400 over the value of the full load 1400. This is multiplied by 100. If we calculated this value, شباب, so it will be 100 over 1400 multiplied by 100, which is 7.14%. So the speed regulation here is 7.14. What is the meaning of that? The meaning is when you load the machine to reach to this speed, okay, the speed has a drop of 7%. Okay يا شباب. طبعا if this value is different for other motors, يعني reach to 50%, this is very bad. Okay, it's like the voltage regulation يا شباب. We said before, voltage regulation reflects how much volt drop are going to be considered or inserted in the machine. The same here also for the speed regulation. If the value of speed regulation is high, this means that this machine is not well designed. Okay يا شباب. So this is one of the evaluation factors for machines.
Doctor?
تفضل.
In the laboratory, they are asking us about the voltage regulation of the DC generator.
Yes.
So I don't recall we have discussed it during the lecture. So is it
actually we did not discuss the DC generator completely. تمام. DC generator because we agreed together this semester that DC generator is not important. Okay. نوع من التسهيل بالنسبة لكم. It's not used anymore in industry, so we don't need to discuss it in our classes. It's make it easier for you. I believe. We omitted about 2 classes from the course. تمام.
But the problem, doctor, it is still in the lab manual, but
طيب هو simply we discussed before the voltage regulation for transformer. So it's by the same concept يا شباب. It's by the same concept. يعني we can also calculate the voltage regulation for DC DC generator by the same concept of transformer. Simply, you have the no load voltage for the generator. If the generator is no load, this means that the output voltage will be the value of generated volt, EA. تمام? And if the generator is loaded to a certain value of load, so the value of voltage output will be VL. So it's nothing but EA minus VL. Refer to what? It's up to the relation. It can be referred to no load or full load. Okay? Up to the relation given in the A-Lab manual. If it is related to no load voltage, so you should divide by EA. Some other references, you may find it referred to the full load or load voltage, so you should divide by V Turner. تمام? So it's the same concept like we made in transformer. Okay?
Thank you.
طبعا يعني the experiment of the DC generator was important in your lab in order to recognize the magnetization curve of the machine. تمام؟ So يعني this is the importance of this experiment, because we need the magnetization curve even in DC motors. يعني we solved one of the problems in DC motors and we use the magnetization curve in order to recognize the armature reaction. تمام؟ Regarding شباب to the parameters identification of machines. طبعا there is يعني an experiment for how we can determine the machine parameters. However, يعني it's not exist in your course here. And this experiment is very important actually, because in order to control the DC motor using closed loop control, and I believe you in 380 course you will have a part of this experiments about how we can control DC motor. However, the identification of the parameter is given in another course. It's called electrical machine 2 or 462 course. تمام? And this experiment is very important because you cannot control the DC motor without getting all of the machine parameters. تمام? However, this experiment is complex a bit and cannot be discussed in our classes here. But we can define the parameters of the machine approximately using some tests like that. One test is called the blocked rotor test, and the other test is called no load test. It's it's the same like what the tests made for the transformer, short circuit and open circuit. However, short circuit and open circuit all of time made for the machines which have electrical output, like transformer, like generators, and blocked rotor or locked rotor and open no load test are made for the machines which have mechanical output, like motors, like DC motor, like induction motor, whatever. Okay. طيب يعني إن شاء الله we'll start in this point in the next class, and يعني I believe إن شاء الله next class we will finish DC motor and start in the new topic. We will stop here and continue إن شاء الله in the next class. Is there any question يا شباب؟ Any question يا شباب؟